Hello everyone, I'm Swati Mohanty. I'm from IIT Hyderabad and I'm going to present my work on micro-electrode based MoS2-Aptamer Functionalised Electrochemical sensor for trace level cadmium detection in water. So in this, I'll take you through the introduction, why heavy metal is a concern, what are the challenges with the current method of detection, what we are proposing, and a look at our results. So, as we know, the population today is growing at an exponential rate, which is increasing the pressure for all the anthropogenic activities, as a result of which there's pollution in manifolds, be it water pollution, soil pollution, or air pollution. Water pollution is one of the stemming issues, which can be polluted by various pollutants like pathogens, pesticides, minerals, salts, or debris. Out of all the minerals and salts, the heavy metal ions pose a great risk because they are non biodegradable. They keep accumulating in the food chain and cause several diseases or affect the human health. Cadmium, for example, is one such heavy metal ion which can cause respiratory, pulmonary, or even skin rashes. And thus, we need to have a system to check or monitor the level of such heavy metal ions in water. For this work, we have chosen cadmium. So the problem over here is these heavy metal ions are mostly in colorless, odorless form present in the water, which go undetected by naked eyes. So we need some highly scientific instrument with precision and accuracy to correctly quantify and detect these metal ions in water. And so we depend on some lab based sophisticated analyzer to get us accurate results. However, the research has evolved and we have some commercially available sensors like the electrochemical sensors, which is predominantly the glassy carbon electrodes, as we know is most reported in the literature, which has very nice sensitivity and accuracy and also has the probability or to get it miniaturized to make a in situ applicable system. However, one great limitations of glassy carbon electrode is that we always need to clean the electrode for the next sensing cycle. And as a result, the electrode, we cannot modify the electrode permanently. There has to be, each time we have to modify the electrode. Mostly we depend on drop casting method to modify the electrode, which leads to leaching during subsequent sensing cycles. Also, it's a lab-based setup, though we can have a miniaturized one, but mostly we are having a lab-based setup. So in order to address these kind of problems, we have designed a compact chip, silicon wafer based chip with 3 electrodes on a single chip and a counter and reference electrode on the same platform. So here we have designed each electrode area, that's the circular areas which you see over here. These are the working electrode areas and these are IDs. As you can see over here, these are IDs with having 1 micrometer gap within the adjacent fingers of the electrodes. In this work, we are trying to modify just one side of the comb to do all the sensing over here. And on top of these electrodes, we will try to functionalize aptamers. Aptamers are single-stranded DNA structures, antibody-antigen reaction, which have been reported widely to have a very good sensitivity and accuracy. It's a good alternative to antibodies because they have higher stability and affinity. Antibodies tend to degrade at room temperature and have many temperature related concerns, while aptamers do not have these concerns and can be used for field deployable sensors. In order to fabricate these kind of sensors, the steps we have taken is we try to electrodeposit the material on top of these working electrodes, which will help us to remove the leaching step, which was a major concern in case of glassy carbon electrodes. Next, we are trying to modify the material with the aptamer by using the EDC NHS and surface functionalization chemistry. The amine-terminated aptamer is cross-linked through EDC NHS cross-linker to the material to prepare the sensor. And now, how do we go about electrodepositing the material on the electrode? So these electrodes are gold. The base of the electrode is gold fingers. And to electrodeposit, we are preparing a precursor solution of our material, which we want, that is MoS2. So for molybdenum, we are taking ammonium molybdate. And for sulfur, we are taking L-cysteine as the precursor. And we are preparing a solution and running a chrono-amperometric setup where we are applying a negative potential of minus 1.1 volts for 60 seconds, where the ammonium molybdate and L-cysteine react in a mildly acidic solution to form a layer on the electrode fingers. The advantage of electrodepositing is that we do not face the leaching challenge over here. We can have a very finely tuned deposition on the electrodes, and we can control what length, what depth, and what type of deposition we want over here. Now, to confirm that the deposition we did, or the precursor which we used, we did a SEM characterization. And as we can see, we are depositing the electrodes only on one side of the comb. These are interdigitated electrodes, so we are using just one side of the comb. As we can see over here, this electrode is not affected, while this one seems to have undergone a slight change in the morphology. And when we do the EDS analysis on this one, we see a sharp gold peak. So there's no other element deposited on this. While when we do the EDS on this one, we see a peak at 2.3 kV, which is well reported in literature to be the peak for MoS2. Now, having confirmed that we have electrodeposited MoS2, we functionalize this electrode with a cadmium aptamer to perform the electrochemical sensing. Now, first of all, we have observed a change in current with the bare electrode. After depositing the MoS2, the current increases, the peak current using the cyclic voltammetry. This is because the conductivity of the electrode increases by depositing the molybdenum disulfide on top of it. Further, when we modify the electrode with our aptamer, it forms subsequent layers on the material, as a result of which the conductivity decreases and the peak current has reduced at the aptamer level. Now, we have been talking that we have been able to eliminate leaching and get a uniform current level, as it was not very convenient to get in case of GCE due to the drop casting variability. So for that, what we have done, we have taken the current of this aptamer functionalization level for 6 different electrodes, and we see there's a variation of only 15%, that is around 4 nanoamperes of current. So we are able to get a uniform current level after the aptamer modification. Now, in order to do the sensing, we have observed the peak current using the differential pulse voltammetry technique. And what we observe is after the aptamer step, when we incubate the sensor with a spiked concentration of DI water with cadmium ion, the current level decreases. As we can see, as we increase the concentration, the current level further decreases. Why does this happen? This is because the aptamer goes a conformational change in its structure when it binds with heavy metal ions. So this change in the structure restricts the electron flow at the interface, because of which the current level goes on decreasing. Now, using this, we have performed this set of experiment with replicates, and we observed the calibration curve to have a very linear form. And we obtained the LOD to be 1.3 nanogram per liter, while the safe limit for cadmium is around 5 to 10 microgram per liter. We have obtained the LOD to be quite lower than the safe limit. And also, we tried to use this sensor on our real samples. Well, this is our blank sample, DI water, which has no ions. This is the response with DI water. And then when we check it with the tap water, there's slight increase in the response. This is because water in itself has some minerals or salts present in it. So there would be a slight change. And then when we have tested with the lake water from the lake near our lab, we find a response has shifted a bit. But still, this response is quite lower and almost less than half than the safe limit, which is 10 microgram per liter for cadmium. Now, with this, we have designed a compact electrochemical setup, which can be used for in situ application for heavy metal ion detection. We could control the deposition, and we have got a very good inter-device uniformity, and the sensitivity and LOD of the sensor are as shown over here, which is well below the safe limit reported. And this is a collaboration work between IIT Hyderabad and Tyndall, which has been supported by Infrachip. That's it from my side. Thank you.